thank you very much, Wilken, for the organization of this event and for the introduction. Welcome everybody. I'm very happy that you are here today, and so that we can get to know a bit better together the atom probe tomography here. So, alors, does it work like this? I will. So atom probe tomography, I don't know how familiar you are with this characterization technique. So I will just briefly go through several characterization techniques that you might be maybe more familiar with, and see how they complement each other in terms of the resolvable features size. So what kind of features in terms of size can we really see, image, or detect, and in terms of detection range. So this is more in terms of chemical information that we have. So how precise are we in terms of the chemical composition we measure? So we have, of course, the TEM in the STEM mode. So we have EDS and ILS that we can use to resolve very small features down to less than one nanometer, let's say. But we still have this error of 1% when we use especially EDS. So we can use SEM to resolve features that are between 10 nanometers in the best case, up to 1 micrometer. And the nanosims here, we can really reach a very high sensitivity in terms of chemical composition that we want to measure. But we are quite limited in terms of the size of the feature we want to analyze. And atom probe tomography just lays here, so which enables us and allows us to see very small features and still get a very good information in terms of chemical composition. So with atom probe tomography, we measure the chemical composition, but it's quite complicated to have the crystallographic information. So we cannot, so in some cases, we still have the poles, the crystallographic poles that we can use to reconstruct the lattice and see the orientation of the defects, but most of the time our materials are heterogeneous and we lose this crystallographic information. So if we let's say start with the basic information that, okay, we just have the chemical composition, we need to always complement atom probe tomography information with TEM data and TEM analysis. So here there are more and more studies made on atom probe tomography samples, first on the TEM, and then we bring the same sample to the atom probe tomography to get this chemical information. So atom probe tomography is a destructive technique, so we still need to always start with the TEM analysis. So how does it work? I will briefly explain the principle of it. So here, with atom probe tomography, we really rely on the model of the isolated charged conducting sphere, in the free space. So we know that the electric field, electrostatic field in vacuum is reversely proportional to the radius of the sphere. Our sample has this shape and this size in terms of the apex of the tip here. So it's a needle shape specimen or a tip. So we simulate that our electrostatic field at the end of the sample will have so the voltage that we apply to the sample divided by the radius of curvature here, and then of course there are some corrective factors because we don't of course have a sphere but let's say a cone. But this is just the basic of it, the basic principle. So the message here is that in the end, the less is the radius of curvature here, the higher will be the electrostatic field, and the better we can evaporate and sublimate atoms. So that's why we need very, very small samples. Here it will require to always have a radius here of less than 100 nanometers. And the volume that we are analyzing at the end are typically of 500 nanometers by, let's say, 50 by 50 nanometers. I will show you some examples afterwards. So once we have our sample ready, I will show you how to prepare this in a slide later on. So we put our sample here in the analysis chamber in front of a counter electrode. Then the sample is cooled down to temperatures less than 80 Kelvin to really put aside any thermal effect. And we apply a voltage, so a DC voltage to the sample. And so this voltage is positive and we have the negative voltage here in order to create a potential and in the end ionize the atoms at the surface of the sample and then eject the ions thanks to the reverse to the potential, and the ions that are emitted from the sample are detected thanks to this position sensitive detector. So we also want to know when one atom or one ion is ejected from the surface, to which type of ion does it correspond? What isotope is it? What element it is? And thanks to this TOF, time of flight that is measured from the time exactly when the ion left the specimen to the moment that it reached the detector, we can calculate the mass of the element, even of the isotope. So, so we have the X and Y coordinates of the detector, and we have the element. We know to which element the atom corresponds. And thanks to this, then we can reconstruct with an algorithm and with a specific software the volume that is being analyzed. Another thing, so in order to know exactly at what moment the ion left the sample, we use some pulses. So we have two modes in this, with this technique, which are called the voltage mode and the laser mode. So the voltage mode just means that additionally to this DC voltage, we will add a voltage pulse that is typically 10% to 15% or 20% of the DC voltage that we have. So this is exactly to create an impulse, a pulse on the sample and induce the ionization and the evaporation of one atom at a time. So in this case, we know exactly when it leaves the sample. The second mode is the laser pulsing mode, which is, so in the case of fragile samples, for example, we can, instead of using these high voltage pulses, which create a lot of stress to the sample, we can use this laser pulsing mode in order to add a thermal energy. In this case, so typically this is used for semiconductors or fragile metallic samples. I will talk briefly now about the kind of ancestors of atom probe tomography here. This is just because we can really see the surface of the atom, of the samples here in terms of atoms. So each dot here corresponds to one atom, and we can really see the terraces and the different crystallographic poles. So this is called field ion microscopy. It's not atom probe tomography, because with atom probe tomography we really evaporate the sample itself. It's a destructive technique. With this technique, the sample is, okay, it's our sample, but we fill the chamber with a gas. And the gas, in contact with the sample, will get ionized. So it's a very high voltage that is applied to the sample. So even if we use noble gas, so xenon, for example, or argon, it still gets ionized, but it really requires high voltage here. So this is typically what will happen during an atom probe tomography analysis, even though this is not atom probe tomography, but this is really, like we can see it better here, we can see that every atom gets ejected, expelled from the sample, one by one. So to prepare one sample, we have two different techniques. The first one is just a conventional electropolishing technique. So we have here a platinum ring that is typically 5 millimeters in diameter, and we have our sample that is cut in the shape of a parallelepiped or a cylinder, and so we can see it better here. We place a drop of an electrolyte that will stay in the platinum ring here, and then by also applying a voltage, we go back and forth with our sample, which gets electropolished until we reach a very small radius of curvature here. So this way of producing sample is fast, but we cannot really know at which feature or where we are in the sample really. So we just electropolish it randomly and then we see what is inside. If we want to have a control on the zone that we want to analyze, then we need to use a focused ion beam. This is what we use here typically. So I don't know how familiar you are also with focused ion beam. It's just an SEM that is also equipped with an ion beam. It can be a gallium beam or it can be a xenon plasma. So we have typically our sample, and with the ion beam that we have, we mill and we sputter our sample in a controlled way, so that we will create a trench here and lift out a piece of our sample. So yeah, this is typically 20 micrometer over 2 micrometer here, and here we can have several atom probe tomography samples inside. Each sample here will be placed on the silicon post, we call that. It's made of silicon, so we will see it later during the lab tour. It's a silicon post on the top of which we will weld our material with platinum. And then, so we have our little chunk that looks like that. And then still with the ion beam, in our case the plasma, the xenon plasma, and with specific rings that we set on the fib, we will little by little mill the sample until we reach this very tiny sample at the apex. So with a radius of curvature of, let's say, 50 nanometers. So this way, so we have several samples at the same time. It's a little bit more time consuming. Let's say half a day. We could make 6 samples in half a day if we are fast, and if there is no problem. And what is important with this technique is that then we can really select the zone that we want to analyze. If we want to analyze a grain boundary, then we can just choose the type of grain boundary or the phase that we want, and we have it. So I will give 2 examples here. The first one is talking about grain boundaries. So we wanted to understand which elements segregate at grain boundaries in an aluminum lithium alloy here. So these aluminum lithium alloys are, let's say, advantageous for aerospace applications because they are very light, and in this case they present quite good mechanical properties. There have been some tests performed on this material of interest, which are fatigue tests here, and then we had 2 versions of the material, one that is naturally aged and the one that is overaged. So naturally aged is just like at room temperature, because we expect that the material would change at room temperature because of the lithium. It's so light, and even at room temperature it can migrate. In the overaged case, so this one, the T84, it would be, let's say, a thermal treatment up to the point of the mechanical properties after reaching the peak of the performance will start to drop. In the case of the overaged sample, so the test is performed in this direction, so we pull the specimen like that, the crack starts to propagate here in this direction, and then in all the samples that we had, the crack just bifurcates by 90 degrees. So we did a lot of analysis with EBSD, TEM, in order to understand what make this bifurcation here possible. So as I said, yes, with different techniques. I'm not showing here all the details and all the results. Just by TEM, we noticed that at every grain boundary, some specific grain boundaries at a certain over a certain angle of misorientation, we have this free zone, a precipitate free zone we call it, that is on one side of the grain boundary. We have absolutely no precipitates. And combining these data with the type of grain boundary, with the misorientation angle, we could still not really understand what really induced this precipitation, this bifurcation. And that's why we performed atom probe tomography analysis here. So this is the naturally aged sample, where we didn't see any bifurcation. So the crack just propagates as expected. So we could really choose the grains here with a certain grain boundary. And this is typically the data that we get with atom probe tomography with distribution of copper, lithium, magnesium, and silver. And these are the results that we got in the case of the overaged sample. And we see that, okay, in both cases, we have grain boundary enrichment and grain boundary segregation of all these elements. But if we have a closer look here, and if we really measure the composition of each element, we see that in the case of the naturally aged here, we have a segregation that is much, much less than in the case of the overaged sample. And with this and with some other investigations and calculations, it was possible to make the correlation between the type of grain boundaries, the segregation, and the presence of this precipitate-free zone. I come to a second example here, which is about steels that are additively manufactured. And we wanted to understand the sequence of precipitation of the carbides in this case. So additive manufacturing, so in this example, it's laser metal deposition. So we bring a powder that we melt with a laser here, and we construct layer by layer our sample. Every time the laser comes, it remelts the layer that is below, or it tempers it, depending on the distance between the laser and the layer that we consider. So what happens is that this is the first layer, second layer, third layer that we deposit. And with the time, we see that there is a heat accumulation in the zone that we consider. Here, let's say, for example, it will be a melting, a remelting again, and from this point, we will start to have, for example, rheostenitization or a phase transformation here, and or tempering. And all this will create a very heterogeneous microstructure along the whole sample. For example, here we can have such a microsegregation here, and here it starts like the presence of second phase precipitates here, depending on where we are in the sample. So in our case, we did a laser metal deposition sample in the synchrotron at DESY. So yeah, we have this node, but what was important here is that in the sample we had 5 different positions of the synchrotron beam so that we could track in situ the formation of the phases. So in this case, we were interested in the carbides. So we know, and we did also TEM analysis, normal SEM analysis, and so on. We know how the microstructure is different, but we don't know ex situ what is the composition of the carbides. So we have the theoretical stoichiometry and which type of metallic elements they might, for example, contain. So chromium carbides, for example, we know that it must be chromium with carbon, but with substitutional elements such as like iron is the main element here, we don't know if it would be pure chromium or pure iron or a mix of it, and so this would give us information about how far we are from equilibrium. So that's okay. So, before showing this, so our sample is this one. So it's like a wall. We see it better here. And here we must consider, okay, that this layer is the first one, so we go in this direction. So this was the first layer, and this one was the last one. So this region here was directly quenched. So when the layers here were deposited, they were directly in contact with air, but they didn't. They were not heated up again and again like it was the case for these ones. So we have here different regions. That here is the quenched martensite, so it's a very hard material here that was directly quenched. Here we would have the accumulation of heat because of the heat coming from the layers above and the heat that would still be here in the layer on the bottom. Here is a zone that is still tempered, but it has the substrate on the bottom that could evacuate the heat. That's why in the middle we have the severely tempered region. And in all, we have three main regions here that we can easily see also with atom probe tomography. So I start here by showing you some results on the last layers. So here we have the distribution of carbon and the distribution of here vanadium. So we see that carbon is segregated on some planar objects, which can be just austenitic films. So when the martensite is formed, it pushes the austenite as these films. And this is just a typical observation that we have in martensitic samples. When we go a little bit, let's say in the previous layers that were a little bit tempered, we also have this carbon segregated on planar features, but we start to also see some precipitates here or some vanadium clusters here. If we go in the tempered region here, the severely tempered region, we see this very, very clear vanadium and carbon clusters here that correspond to vanadium carbides. And then if we go to the layers that were first deposited, and in this case so the moderately tempered regions, then we still have we still see those vanadium carbides, but they are much bigger than the other ones we saw here, for example, and even a little bit bigger than these ones. And this shows exactly here the effect of the time that we had. Even though this region was not tempered as severely as this one, it still had much more time to let the atoms diffuse and induce the coarsening of the precipitate that we have here. So this was an illustration of the typical information that we can have with atom probe tomography, and of course, there are in all metallic samples we can apply this technique. There will always be a little bit of information about what type of precipitates we have, which will evaporate at a different field, for example, in a different, like with a different field as compared with a matrix. So this may cause some artifacts, of course, but if we know that this is happening, we can correct this. In the case of carbides, this is actually the case because the carbides have a very specific field of evaporation. So when the voltage is applied to the whole sample, the carbide is just on one part of the sample, and then we will have some like a difference in the speed at which the sample is evaporated in the matrix and in the carbide. So yeah, there are of course some artifacts like that, but we can of course correct for them and still rely on the results we have from atom probe tomography. Yeah, so this was my last slide, so yeah, please don't hesitate. If you have questions, I would be happy to take them and try to reply. I hope this was clear for you. And yeah. Thank you.
First of all, thank you very much.
Welcome.
Do you have any questions? I actually do have. Okay, maybe you start.
I do not understand how you get the precise 3D information. You evaporate atoms from the tip, but how do you know like which layers are gone?
So we have in the raw data file, so we have the X and Y position on the detector, and we have the time. With the time, together with the time, we have the frequency of the laser or voltage pulse. And with this, we can, thanks to the evaporation field at the surface and thanks to the main element that is there, so we know the evaporation field of each element, and thanks to that, we know exactly at which evaporation field did this element evaporate, and then reconstruct with the mass. So it's with the TOF, the time of flight, and the distance between the sample and the detector. So the distance changes between the sample and the detector. That's how we reconstruct it. No, it's not clear.
So you have like, a main element in the matrix, and this arrival time drifts. This gives you a signal of the depth that you're analyzing.
So the field we put normally is still the same, but the voltage that we apply increases with the time because the sample gets larger and larger. So to keep the field to enable the evaporation, we need to increase the voltage. And thanks to this, we know how much distance we have between the sample and the detector. And that's how we reconstruct the Z direction. It's just with the voltage in the end.
Trench like out of copper there, and the other thing is carbon or something, then one of them will be evaporate faster than the other. So you will not get this really shape like cutting off layer by layer, but you will have some deformation that.
Yeah, this is one type of artifact. If we have an heterogeneous sample, we can have one phase that is evaporated faster. It won't be in such a case that we will have 10 nanometers of difference. It would never be the case because the samples are still like so small that the electric conductivity is still happening. So even 1 nanometer would not happen. But yeah.
So this is regarding the sample holder. Is it always in the form of a pipette, or you can have it in some other form also?
Yes, it has to always be in this shape of a needle. So we had this problematic actually recently. We had these powder samples. We needed to compact them very much so that we would reduce the porosity inside. And then from this packed sample, we extract samples for atom probe tomography. So with the ion beam, we cut all around, and then we put them on this silicon pores that I showed, so this little like kind of pyramid. And then with the beam itself, like the ion beam, we will mill all around. We sputter, actually. We sputter the material as a circle all around, so that we will get a very thin apex and a very thin needle at the end.
But in that case, if I understand correctly, like a single grain of the powder would probably still be too big for atom probes, so that's why you mill it and then and sputter it like this?
Yeah, so if you have micrometric grains, for example, yeah, you will have only one grain in one sample, yeah.
To what extent does this technique, like for example, there are some lightweight materials, for example, helium or the hydrogens, when you are applying the voltage and then the ion will be ejected, then how can what efficient is that the detector can detect those things, the lightweight materials?
So the detector is constituted of microchannel plates, and 50% of the surface of the detector is covered by this microchannel plate. They are used to multiply the signal that we get by one atom. When one ion reaches the detector, the signal is transformed into 10 to the power 5 electrons. And then we know, okay, one ion reached the detector. But since they cover 50%, then the detector efficiency is only 50%. So we get 1 ion over 2, but still it is everywhere. So this detector is covered homogeneously, so it doesn't have any impact on, for example, the light materials will be less detected, for example. The concentration we have is still correct because it's like every element is impacted the same way. Yeah, it's not like EDSA because we have not the same excitation of light atoms and then we don't detect them well or with a bad accuracy, for example. This doesn't happen. Here we detect all the elements with the same accuracy. Except hydrogen, because hydrogen is a big issue, as even if the analysis chamber is in a very good vacuum, very low pressure, we still have hydrogen inside, and when the sample is subjected to this voltage, the hydrogen atoms around would get ionized on the surface and then evaporate, and then we would detect them as coming from the sample, but they are not coming from the samples. But yeah.
You said that you could also resolve the isotopes. How well can you resolve them?
Oh, we see them very clearly. So that's a pity. I should show them, but you really see the peaks of each, like in TOF SIMS, for example, you have really one peak for each isotope. And the resolution is enough to see them.